Все поставили, да? Проверьте, что работает.
Ну вот сегодня мы начнем с Ле Мартина Риса, это такое вспомогательное утверждение, ну, мы к ней постепенно подойдем. Так, но как бы она очень важная, в общем, я попытаюсь пояснить, зачем она. So let us consider the following problem. Suppose our ring is graded. So A is graded. So this means that A is equal to the sum of its components, where I is bigger or equal to 0. And you have the following property: AI times J sits in AI plus J. Yeah, so the example that we shall keep in mind that will be crucial for our studies today. So basic. Yeah, so of course the most basic example of this situation is polynomial ring, of course. Yeah, so that we have x0, xn, and also so naturally we grade the variables as of degree 1, but you can give arbitrary degrees to variables. So just so some alpha j. So you can decompose the ring into the graded pieces. Yes, so corresponding to the gradings. So this is precisely will get the sum of some ai's, where f belongs to ai if a degree of f is equal to I. And you calculate the degree naturally, and so here we assume that it is homogeneous with respect to the variables. But also you can, so with respect to this grading, so all monomials of the grading has the same grade. So, but the basic example that is we shall keep in mind is not this example, but the following. So just here. So you can start with A and start with some ideal inside A. And you can consider the powers of this ideal, and you can form the ring that is the sum of the powers. So alpha I, and alpha is big or equal to 0. So we assume that AI A0 is just A. So the ring itself. So this ring is substantially larger than the ring, and of course we think of the product that the component AI sitting here times AJ sitting here. It sits inside the AI plus J component. Yeah, so here in the decomposition we have AI plus J. So the product is not in the same ring. It goes like degree goes. Yeah, like with the corresponding I. And here, of course, the inclusion is strict. Yeah, so you have equality here. Yeah? So notice that you may do the same trick with symbolic powers also. Yeah, because just we shall see at the exam that for symbolic powers you have inclusion. Yeah, so for symbolic powers, so you have a Pn Pm sits inside Pm plus n.
And also, so here, if you think of this condition, yeah, so naturally you have equality when, so here you have this equality from the beginning, but also you can introduce graded modules and filtration of graded modules. So M is a graded module. And here, of course, since so here you can think of for some kind of generalization, you may think that the filtration is just bounded from one side, for example. Well, here the filtration is positive on the ring, and in order that to make so where we should put the unit, we should put the unit in the zeros component, yeah, because the unit shouldn't move anything. So at least so the ring should have zero component, and then if you want the filtration to be bounded, we have only choice to start with zero. And if you think of modules, you shouldn't start with zero, so you can start with negative grading if you wish. And the condition for consistency of the ring and the module is almost the same. Yeah, so AI times mg sits inside mi plus j. Great. So this is just about gradings in general. So also we can think about filtrations and on the same modules, and so two filtrations on them. Oh, sorry. Yeah, so we can think of the same two filtrations on the same module, so on M. And why we bother about filtrations? Because yeah, so actually because somehow we may think about p-adic rings and they also have this kind of filtrations with maximal ideal or with prime ideal, so you can think of start of Z, so you can localize, for example, by prime ideal P. And so here you will have filtration with respect to the powers of P, and here on p-adic numbers you may think about convergence. Yes, so convergence for the series, we think of having AI PI, where AI can be just the representatives of remainders, so you fix the... Да? Но ZP вообще, ну, как бы можно стартовать с локализации, да, исходно, а потом пополнить. Ну, вот как бы... В данном случае чем? Ну, ZP можно, да, давайте сначала локализуем, да? Вот, то есть дальше у нас возникает расстояние, да, ну, вот я хотел сказать расстояние, что если вы берете ну, какое-то число n, то вы его раскладываете как so if you have n and you decompose into two coprime parts, p and m are coprime, Yeah, so you can introduce the norm on a periodic norm, which is let me put it new p of m is equal to 1 over pk. Yeah. So there are different ways to do it, but in a sense they are equivalent. But sometimes it is more convenient. So in algebraic numbers, it is more natural and more convenient to assign the norm like this, and not, for example, to say logarithm of this number that you assign k. Yeah, so then this gives you a distance and topology. So you know that what means that the sequence tends to 0. Yeah, so the sequence of numbers tend to 0 if they become more and more divisible by p. Yeah. So then you can, as we have discussed, you can take the completion with respect to this norm, meaning that if you have a maximal ideal, you can consider the limit of a mod mi, and this will be if you put if you take ZP, take localization with respect to ZP and take this kind of completion, then you will have periodic numbers as the result. And when you consider periodic numbers, so you can consider the series, more or less the numbers are series where AI are just the numbers from 1 to p, for example, and or negative numbers from 1 to p, and you may form such series and say that so you may see that the series are convergent. Series of this form are convergent with respect to this distance. Yeah? So just yeah. So these are periodic numbers, and why I was saying about periodic numbers, because somehow this, speaking about filtrations, we speak about topology. Yeah, so since we have introduced the norm, the evaluation, so we may think about topology, meaning that the sequence converges to 0 if the norm converges to 0. And filtrations are so somehow you can think of, in order to say that the norm is convergent to 0, you may say that so for this norm it can be taken equivalently. You can multiply by some fixed number this function of norm, and it will give you the same topology. So meaning that if the sequence every sequence that converges in one topology in one norm will be convergent in the other norm. So, for example, if from the viewpoint of the sequence and sequence of ideals, you may think about the sequence that Fi belongs to sufficiently large M Ni, yes, so that Ni tends to infinity. But of course, if you take twice of Ni, it will be also, you will also, and Fi satisfies this condition, yes, so you can renumber, and the sequence will still go to infinity with respect to the other filtration. Yes, so that you may think of, so in order to say that something tends to 0, yes, so the sequence tends to 0, if you have a sequence where its elements belong to some mi in the power ni, which is decreasing sequence of ideals, but you do not bother about precisely about the number of mi, it should tend to infinity. So you see that, for example, if you take natural numbers here, even numbers or odd numbers, you will get the same result, yes, of the convergence. And so the idea is to do it the same on filtrations. So two filtrations are called equivalent. If there exists fixed number and zero, so such that we have two filtrations. Let me put it mi and mi overline on m. Are equivalent if there is a number such that you can bound they're decreasing, so actually what I want that we bound mi mn by by the number m tilde n plus n0. And it sits inside this is decreasing now. So filtration is decreasing, yes, so that for the module, yes, so that you should have here it is n minus n0, and here you think of n plus n0. So you bound each term between two other terms, and in order, so the same should be for m tilde, and this simply can be reformulated that mn contains m tilde n plus n0, and m tilde mn tilde contains mn plus n0. Yes, so that sufficiently large piece of filtration. So
можно спросить?
Да.
Вот вы говорили о топологии, но то, что фильтрация задает топология, я так понял, она задается так же, как на периодическую часть.
Ну,
вот мы рассматриваем модуль в двойную сумму и вот задаем методы по типу.
но только как бы тут вот тут я забыл сказать вам, что вот это вот, сейчас я говорил о фильтрациях, вот о неградуированных суммах, извините, я тут как раз вот сейчас я дайте обозначение посмотрю у себя, потому что да, тут как бы давайте сейчас тут можно как-то вырезать, подвинуть, знаете, вот это. Что? Сейчас выделить надо, но вот этот. Ладно, да, ну тут я, извините, я тут как бы перескочил, потому что я I just skipped for a moment because I started with gradings and then passed to filtrations. So let me speak about about filter. So we had gradings, yeah, so we started with еще у меня. Так. Секунду. полная авария произошла. Вот это да. Отлично. Да, sorry, so here is, so we started with graded module, yeah, so started with graded module. But you can think about filtrations, yes, so we can think about its field, so this is filtered by let us call it mi tilde, meaning that the grading j is bigger or equal than I, and you sum up all the terms of j that is of degree I. This gives you decreasing filtration. Yes, so this gives you decreasing filtration. Yeah, just so with the condition that you have a items j tilde sits inside j tilde I plus j, just because the same holds for grading, and just you can recover initial pieces of that you have started with, yes, so that mi is isomorphic to mi tilde modular I plus 1, yeah, tilde. Yeah, so this is decreasing filtration. And when you more generally, you can speak about, you can start with decreasing filtration. Yeah? So you may start with a module and the filtration, and also you can given filtration. So given filtration. On the ring. Decreasing filtration on the ring. And on the module, yes, of course, for the module, you can always shift the filtration whatever you like, because this condition, I mean, if you look at the condition for module, you can add everywhere the same number, so the module also will give you, so we can shift the grading, shift the filtration. That you, so you call the separation n, yes, so that an I, and usually the shift is just so the shift is in this. Yeah, so let me. Yeah, so the naturally the shift is taken in the direction, in the left direction. So you
yeah, so the lower number, so so I's number is I plus n. Yeah, so that the module, from the viewpoint of modules, you are moving or the sequence of modules to the left. Yeah, so you assign smaller number to the larger graded components. Yeah, so if you just look at this filtration, so from the beginning you have a piece where you have mn and it becomes a zero piece. Yeah, so that from the viewpoint of I. Yeah. So this, in a sense, it is a shift to the left. So you may always do the shift, and that means that if you like, you can start the gradings of modules with 0. And here you have so the what what I was saying, that on periodic numbers the topology is given by filtration, not by grading, but filtration. Okay? So that you have, so you are saying that the just AI, the sequence tend to 0 if or even MI. So the sequence of modules tends to 0 if yeah, so that means that for any large n, yeah, so that there exists some number I of n that depends on n, so such that just mi belong to this term of the filtration, mn, if I is larger than in. Yeah, so this is just rewriting epsilon delta definition, natural definition of convergence. And of course, in order to say that something tends to 0, yes, so you keep in mind that the filtration should satisfy the property that intersection of all modules is in the decreasing filtration is 0. So the filtration is called complete. Is called complete. If intersection of mi is equal to 0. And we have example of this situation. For example, you can do it in Z, yeah, so that you have a sequence of ideals p to the power n, or you can take the local ring and you have the sequence of ideals mi, and you have the property that intersection of all of the mi's is equal to 0 due to Nakayama lemma. And then you just then we can speak. So since we think of convergence, yes, so this allows us to speak about equivalent filtration. So as I said, we keep in mind that just that equivalent filtrations should give you the same, so equivalent, the same notion of convergence, the same notion of topology, and this is precisely this definition that we. So sorry for just I have skipped from gradients to filtrations. But gradients are related somehow if you just do not want to speak about filtered modules. So given filtered modules, you can consider
graded module, and so Riesz ring. So this is called Riesz ring. So also, if you have so there are two things. Sorry, there is a notion of graded ring. So given filtration of A on A. And on some module L, similarly. Yeah, so you can consider the following. So you can consider associated graded ring. So this is called the graph of A, which is just the sum of quotients of filtration. So that you can think of AI moduli A. I plus 1, the note that the filtration is decreasing, and the same can be made with the module. So this is called associated graded. This can be done in either commutative world or non-commutative, and maybe, so I wouldn't say that in non-commutative it is more important than in commutative, but nevertheless it is very frequently used. So it's even just even some I would say maybe even more frequently than in commutative algebra. So if you have these two things, yes, so you can have an algebra in the ring, you can form these two objects. So notice that this is ring, yeah. And if you think of this mi's, yes, so you can, so what can you do? Yes, so if you, so here you can introduce the action of A, yes, so that if you are writing down A modulo mj modulo m j plus 1. Yes, so this can be so this sits inside AI. So so notice that this this is taking representative up to this kind of the element of mj, and you see that AI times mj is so this sits inside m j plus I modulo m so I plus j plus 1. So moreover, you see that if so this I mean that so when you act on this module,
Числителя
да.
I plus j просто. Числителя.
да. Moreover, you see that if you take the elements that live in I plus 1, yeah, so that if you put the elements A that belong to AI plus 1, when you take this the image in the module, yeah, so that if you multiply it by mj, you will sit inside m I plus j plus 1. Yeah, so you see that actually it is not AI that is acting on the module, but the quotient. Yeah? So you see that this associated graded module is actually, and you see that if you multiply AIs on this MJs, it should act from the property of it is natural to. So AI moves just MJs in different component. So it is not the ring that A is acting on MJ, but of graded MJ. But this is graded, associated graded ring is acting on graded modules. So note that A is not acting on graded of MG, but graded A acts. So this is the way to construct associated a graded ring out of filtrated objects, and also you can do it a little bit differently, and this is called Riz ring. So Riz ring. So given the decreasing filtration. Yeah, so I'm rewriting all this definition because I realized that it is hard to distinguish between in the notation between grading and filtration. So each time, not to make the confusion, I shall do it. So you have this Riz ring, and Riz ring does the following. So you can form the following ring. The sum of AIs, and then this is just the ring that we considered. So when when AI are given like A in the power A, so we have the ring that is the sum of ideals. So if you will learn algebraic geometry, so this will be related of the operation of blow-up, but just you should just think of it a little bit. So there are some details that should be covered here, and also, so let me call it like this again. Sorry for. So we shall not consider completions. So this is not completion. So not completion, but it is an operation that gives you. This kind of ring, and the same can be think of thought of modules. So you can form the module that is with decreasing filtration, and this module will be the module of this ring. So why we are doing this? So the aim is to study Hilbert polynomials, and also what about filtrations. So also mainly we shall be interested in this kind of ring. So suppose now that our ring A has this kind of filtration with by. So AI is equal to the powers of ideal, and now we shall now we shall be speaking about stable filtration. So Yeah, so we call mi on m is called the A filtration. Oh, well, simply if it is related with, it is a filtration that is associated with precisely I, so if A times mi sits inside the mi plus 1, and it is called a stable, so it is if there will be large number, if there exists n0.
А это уже исключительно все для фильтрации, где мы рассматриваем степени идеала.
Да. Ну, теперь, ну, можно сказать, что фильтрация мыта, ну, стабильна относительно аитах, фильтрация аита, да, ну да, давайте я скажу в общем случае, да, но как бы, so let us call it like this. So filtration is called the AI stable if there exists the number n0 such that AI m j is equal to m I plus j for I bigger than n0. То есть, no, and for ideal, this will mean that, sorry, for j is bigger than n0. So for j is strictly bigger than a0, and so it is called a stable. If there exists n0 such that a times m j is equal to m j plus 1 if j is bigger or equal than n0. So this is the notion of a stable filtration, and just the following is just so the following proposition is easier. I will omit the proof proposition that this is condition of just so this is a proposition about graded ring. So let A be a graded ring. So it is Noetherian, then the following is equivalent. Statements are equivalent. So first of all, A is Noetherian. Yes, so let me put it. So A is Noetherian. And the second, that of course, this is the property of the graded piece. So the main graded piece is 0 because everything is each i's are graded pieces over A0. So you have to assume that A0 is Noetherian. Note that the subring of Noetherian ring can be not Noetherian. So A is Noetherian, and A is finitely generated over as the ring. Over A0. So meaning that you have over A0, so meaning that you have the collection of elements A1, AK, and the natural map to A is surjective. So the map from, so any element of A can be written as the polynomial in coefficients in some fixed graded elements and coefficients in A0. Yeah, but the most important for us is the following, that the following condition of saying that that filtration is stable. So let just criterion, criterion of stability of filtration. And it is yeah, so it is done as follows. So suppose A stability of filtration on M. Yes, so on M. So suppose you start with again you start with filtration, decreasing filtration, and you have AMI seats inside the MI plus 1. Yeah, but you want to check the stability. So let us first form just an ice. So the collection of modules. So this is of course collection of not A modules but A0. Yeah, so this is collection of A modules. Yeah, so collection of A modules. Meaning that A acts on each factor here. But also, yeah, so...
Сейчас у нас снова A это уже степень идеала.
А это, да, А у нас пока кольцо, да, ну и фильтрация в А это степень идеала, да. Вот такой, да. Соответственно, мы смотрим, ну, как бы, вот это M это модуль над А. Вот, мы как бы можем посмотреть на, ну, вот на такие модули. Это, ну, как бы это А модули. И, but then we may form the following. So these modules, of course, they sit. So they are contained in M tilde, which is the sum of all components Yeah, so, but this is, this thing is a hat module, which is the sum of AIs. But this NIs are not submodules with respect to this ring. So you multiply each MI by the elements of A, yeah, because MN is filtration on A, yeah, so that MN maps to MN when you multiply by the elements of A.
Сейчас можешь спросить?
Да, да.
Вот МТ, я так понимаю, сумма от 0 до N, МН или может там это?
MN. Спасибо. Ну, да, тогда бы я просто MN поставил бы сумму сверху, ну, как бы без вариации индекса. Вот, соответственно, ну, как бы вот эти вот MNT, они именно A подмодуля. Ну, потому что A сидит, so A plays role of A0 in this A hat. So A is equal to A0 equal to A in the degree 0 here. Yeah, so that you have the collection of A modules inside a hat module. And also you may form an hat which is just you take these modules and generate the submodules by a hat. So denote. So now this is collection of a hat submodules. And they look like the following. So you have components from M0 to Mn. Yeah. So of course, because N is sitting there. And look what will happen if you allow to multiply not just by 0, but higher terms, AA, AI, etc. Yeah? So you will have the following variables here. So then you will get just yeah. So since AI MJ sits inside MI plus J, yeah. So you will see that the largest component that can be seen here is just A times Mn, A square times Mn, etc. Yeah, so you are taking the last component and the equality. And this stabilizes the last component. Just because for these guys you have this natural inclusion. Yeah, so that if the component has lower number, it you can write it down like this, yeah, so that you can write it like E times G if G is less or equal than N. And for E you can take the complementary, yeah, so that N minus J here, yeah. So it will lie. Yeah, and here you can put K, yeah, so it will lie inside a K, so this is just, and this will lie inside the Mn, yeah. So you see that the largest component that can stand here is just Mn times AK, yeah. So this
so you get this kind of collection of modules, and assume that M is Noetherian. So assume let me write down that note that Mn is a finitely generated A module. So this implies that M hat is a finitely generated A hat module. And you may get also if you take the union of Mn, so the union of Ni hat. It is just notice that this is the increasing sequence of modules, and in the end of the day you will get the sum of all modules. Yes, so just you will. I mean, even for n you will get the sum of all modules from 0 to n. So you will get that it is just m. So assume that M is Noetherian, M hat is Noetherian. What you will get? You will get the stabilization of the chain that that gives you M, so that this will imply that Ni chain Ni stabilizes, increasing chain. Stabilizes. But what does it mean for us? Yes, so that means that when you compare these two modules, so you will have M0, so stabilizes for large K, large M0. So this this will give you that on the step. So if you write down how does they look like. So you stop at n for some module and you have A, M, n, etc. A square. Yeah, so this is the module n hat. And you may write down the module n plus 1 hat. So if you think that they are equal, so if n is bigger than n0, so you will simply see that so the beginning of this sequence is the same. So here for n plus 1 you have m n plus 1. So, and here I do not bother, it will be a power a times mn plus 1. But what is important that you will have the equality, so you will have this condition of graded pieces. So this implies that that m n is equal to n plus 1. And this implies that filtration stabilizes. So filtration is stable. Yeah, so also you can think of the same, I mean, I have used A, but alpha, yeah, so the ideal, but you can think of stability with respect to more abstract filtration with AI. Yeah, so simply you will have A1 here, here you will have A2, etc. Yeah, so that in the so here you will have A1, man. Plus A2, Mn. And the condition will be that this is equal to the corresponding graded piece. And also you will have actually qualities on the same graded pieces here, so that Mn plus 1, etc. Yeah, so you will have also equality here, but on each pieces of this type. But also you have everything for this large n, so this is more or less automatic. So just you can derive it after you know the first equalities for all large n. So what is the benefit of this? That you see that yeah, and you see what? So if you have so if you have vice versa, so if the so what we get is the following. So if M is Noetherian, then filtration stabilizes. And this means that, and vice versa, if filtration stabilizes, so if filtration stabilizes, Mn. So if the filtration is astable on M, is so here I shall write what I mean, that AI 0 is equal to Mi plus N0, or you may think of AI N0 is equal to Mi plus N0. Yeah. So, and vice versa, if filtration on M is alpha stable, is astable, so alpha stable. So this implies what? This implies that the mod at some step the modules n stabilizes. So that means that sequence n hat I stabilizes. So this implies that just m is equal to n hat and n hat, but this is equal to a times an, and this n is finitely generated a hat n. Yeah. So n is finitely generated a module. So this implies that M is finitely generated hat module, and a hat is Noetherian. So it is convenient to assume that it is Noetherian, so M is Noetherian. Yes, so that you have this kind of property. So what is convenient about this picture, that we have reformulated the properties of stability of filtrations in terms of modules, some property of other modules for other rings, but they are the properties of being Noetherian is more convenient because some submodule of Noetherian module is Noetherian, and quotient of Noetherian module is also Noetherian. So as application of this observation is the following theorem. Yeah, so that maybe I should state this as the proposition. Yeah, so that this is proposition. That suppose a hat is Noetherian, then the following is equivalent. Following statements are equivalent. So first of all, filtration of M is a stable, and the second is that module M tilde is Noetherian, well, finitely generated. A module. Yeah, so actually, yeah, so what is more important that it is finitely generated. Yeah. So for us, and if now let us look at the following application. And it is precisely acting with lemma, but we shall state with more general statement. Suppose you have a module M with filtration. Yes, so you start with module M with filtration. And suppose you have a submodule here. So M is a submodule. And what you can do with a submodule, so you can, on N, you can consider two filtrations. So notice that you have conditions that AI MJ sits in MI plus J. And suppose that filtration is stable. So assume that it is stable. So meaning that M1 A1 Mn is equal to M. So MIN is equal to MI plus N for N larger than N0. Yeah? So you can notice that you can consider two natural filtrations here on the submodule N. So so first of all, you can obtain the filtration on N by saying that you have ni tilde. This is intersection of mi with n. Or you can consider the filtration on n simply by inducing the filtration by the powers of A. Yes, so by the filtration of on A. Yes, so you can consider ni as a I times n. Yes, so this is also decreasing filtration. So the question is if these filtrations are equal in general or not, and if they are stable. So filtration. So the question is that can we compare these filtrations? And the answer is positive simply because we can use previous proposition and the property that the submodule of Noetherian module is Noetherian. So we shall prove that. To compare filtrations, it is equivalent. So this filtration is automatically astable. Yeah. And to compare these filtrations, we shall prove that this filtration is astable. So this is sufficient to prove. That MIN is stable. And how to check that filtration is astable? Yeah, so you should do the following. That n hat is a submodule of m hat. Yeah. So M is Noetherian. Then this means that yeah, and if you think of so M is Noetherian. So we have noticed, yes, sorry, we have noticed that filtration on M, so filtration on M is astable. On M hat M is astable. This implies that filtration, maybe it is better to say AI stable, yes, so that to emphasize that we have filtration AI. Yes, so this implies that M, so the previous remark implies that M is finitely generated a module a hat module. In particular, it is Noetherian. And then we can form this the same module, but n hat is so this implies that n hat is submodule of M, so a submodule of Noetherian module. So this means that it is finitely generated, so it is Noetherian. And this implies that it is finitely generated. And we see so this means that filtration is astable. So filtration is stable. So we can. So this means that we can write the following. So we can write that just AK, if you multiply by AK, the intersection of N and I, yeah? So it will sit inside just so it will be equal, yeah, to the intersection of N with Mi plus K for large I, yeah? For any K and for large I, bigger or equal than N0. And you may write this classically as Artin's lemma, so which is refer precisely to the powers of ideal. So that here just Artin's. But in Artin's lemma, you also additionally say something about this stable filtration, Mi plus K. So take filtration on M, Mn is equal to ANM, and put n submodule, A submodule. So you consider induced filtration in I with respect to this filtration on M. So simply saying that this is N intersection with Mn, Mi. It is just A and M intersection with N. And you just rewrite this kind of thing for just for this two filtrations. So this is, so then you are taking n terms of filtration, writing down it like this. So this is just nm, and you can multiply this n minus n0. So then for large n0, so then there exists a large just there exists 0 such that now I simply write down this equality on filtrations just by saying that just this number is bigger, so I can
subtract this n0 here, so that it is a n0 m intersection with n. So this is this part is precisely. So sorry, everything is precisely a n minus n0 times n0 filtration. Yeah? So this is Artin-Rees lemma, and it says the stability of alpha filtration with respect to m. But notice that this more general way to speak. So what we shall be interested in is, of course, Artin-Rees lemma, and so the general way to formulate this kind of things in terms of theorem rings is much easier than speaking about particular case of this Artin-Rees lemma. And if you open the, if you compare books like T.R. MacDonald book and Matsumura, so more or less this is contained in T.R. MacDonald book, so this kind of exposition. And if you compare it with Matsumura, it proves Artin-Rees lemma directly, and it is a little bit involved because so finitely generatedness and the proof that something like Hilbert basis theorem is covered in the proof. So this allows this more general way to look at it, allows us to get rid of Hilbert basis theorem from the proof. And also, yeah, so here just yeah, so let me do the stop here. Let us make a 10-minute break, and after the break we shall speak about Hilbert polynomial, and I shall try to explain why this why these filtrations are important for us, and why it is important to compare filtrations.
Ну, вы же очень общее название, уже начинается.
Да, ну вот давайте теперь поговорим о функции Гильберта. Да, еще, ну вот, so I have a slight remark about the exercise we were discussing. For example, when you are speaking about the ring of the form, there is ring, yeah, so that if you have A is Noetherian, so this implies that A is finitely generated. Yeah. So you have the variables, and yeah, so A1, AN. So you may do the following. So you may generate the ring A. So you have a map from polynomial ring A, where you add the same number of variables as generators of the ideals. and you map it simply into, so you map it to the Riesz ring by mapping all xi's to the corresponding ai that lie in the component that is first graded piece of Artin ring. And you see that the ring is generated, so this ring is generated by A, precisely by ideal A if you add the coefficients A. Yeah? So just over the ring. So notice that Hilbert basis theorem tells us, so Hilbert basis tells you that this is Noetherian, and then this implies that surjective image, so image of Noetherian ring is Noetherian. Yes, image of Noetherian ring. Yeah, so more generally, when we are speaking about more general ring, and so we know the so here we put it in the assumption, yes, that you have yes, so we have taken finitely generated ring over A. Yes, so the submodule of and here notice that we made in the assumption, we put in the assumption that the head is Noetherian in order to guarantee this condition, but for Artin with ring, this is no less. So this is if and only if statement. And notice that also notice that if already a head is Noetherian, then all ideals are also so first component is also it is ideal because it is stable and multiplication by A. So this is ideal. So automatically it is finitely generated. But when you are considering more general rings, so here this ring has the property that it is generated by the elements in the degree 1. So more generally, the rings can be generated by variables in higher degrees. And for some statements, it is convenient to have the property that rings are generated by the degree 1. And there is a specific operation that can be do it, but so here I meet this kind of statements. So yeah, so now let us speak about Hilbert polynomial. So we start again with more general picture, and then we shall, in order to introduce dimension, we shall just choose a specific filtration, etc. But first of all, we start with Hilbert polynomial, and Hilbert polynomial. For Hilbert polynomial, we start with graded rings. And notice that in general, if you start with local rings, it is not graded. But as we have learned today, so there is a way to make it graded, and that will be so our aim is to do the following. So if we want to introduce some kind of dimension for the local ring, we associate with it a graded ring, we apply the theory for Hilbert polynomial for graded ring, and we get some answer. So first of all, so here we assume that AI is graded. M is is a graded module. Now it is graded. Graded module. So MI are A0 modules. And assume that you have lambda that is the function from mi to z. So this is so function that is additive on exact sequences. Not short. Exact sequences. So if you have so if you have k then lambda of L is equal to lambda of k. Plus lambda of L. Yeah, so this is additive for function, so you can form the Poincare series. It's just the sum of these functions on graded pieces. Yes, so this is additive functions on mi, so as so a function on mi, so on each component. And notice that since we think of graded situation, yes, so if the exact sequence of modules, if we want to make it graded, yes, so that you think of exact that it is graded simultaneously, yes, so that graded piece should map to the graded piece. So then this we are taking this lambda on. So let me show the exact sequence of A0 modules. Yeah. So to avoid confusion. Yeah. So then you form this Hilbert functions that is generating series, and
What is t?
производящая функция.
What is t?
I misheard like по-русски. So that means, so what it means in Russian. What is t? T is just some formal parameter. It is generating series. I mean, I'm just considering informal power series. I consider the series with coefficients this functions in Z.
Okay. And K, L, N, are those graded module?
M is graded.
No, in that.
In exact sequence, no. I said the A0 modules.
Okay.
So that
А лямбда на чем определена?
на А модулях.
Ну да, все-таки не изомутово, видимо, она бьет, а
Ну, да.
множество ему.
Давайте, да. Ну да, давайте я напишу. Спасибо. Да, то есть. Теперь лучше. So it maps from A0 modules to Z. So associate to each A0 module, it associates some. So if you think of this function, yes. So we shall use. We shall assume that A is finitely generated. So A is finitely generated over A0. So we assume that just induction, we have induction on the number of generators. Yeah, actually, before saying about induction, I should say what we are proving. So M is finitely, assume that it is finitely generated over A0. So we will prove something about this series. So PMT is a rational function that looks like a polynomial divided by the product and where these di's are degrees of the generators by so I assume that by homogeneous elements AI where degree of I is equal to di. Yeah, so we have by and the number of by S homogeneous elements. So just so you have A is equal to A0, A1, AS. So this is a rational function where you can read off the generators via this denominator. Of course, you may think in this formulation of the theorem. Yeah, so just. Но у нас градуированная алгебра, поэтому, ну, как бы А и Т принадлежат А, Д.
Ну, то есть где лежат, да?
Где лежат, да. Вот. Ну, просто, вообще говоря, образующие могли быть неоднородные, да, ну, как бы говоря, что наша алгебра, конечно, порождена, да, но мы не требуем, чтобы в определении образующие были однородные, но любой образующий в градуированной уже алгебре, да, можно представить суммы своих градуированных частей и взять излишнюю в систему, то есть в качестве образующих то, что составляет наши элементы. Да. Все градуированные элементы. So note that here, of course, so in this, so the algebra A can be, да.
Если мы берем какой-то элемент, который нас изначально порождал, и теперь мы хотим взять
Но вы хотите
все
просто
градуированные элементы, сумме которых он равен.
Да.
У нас не может получиться какое-то большее?
Да, конечно, может. Вот я сейчас об этом.
Все, хорошо.
So note that in general you can, for example, have repeating generators or dependent generators in the sequence. But notice that for formulation we do not care about this because so the denominator will be larger, but still f is a polynomial. It can be divisible by the parts of the denominator. So at least you see that so this doesn't. If you divide the numerator by denominator, so I mean if you cancel the same terms, you will see that at least you will see that if a denominator still remains, that some of the generators cannot be thrown away. But of course we do not speak about the following, that if a generator can be cancelled, then you can throw away it from the generators.
Сейчас еще можно один вопрос?
Да.
Что такое однородные элементы?
Ну, просто мы говорим, что элементы из, ну, когда мы говорим о градуированной алгебре, вот элементы из АД, это мы их называем однородными. Ну, как однородные многочлены? Однородные многочлены — это те, которые
То есть это...
при умножении всех переменных на t многочлен умножается на t в степени t, правильно? Ну, в однородных многочленах. Ну и как бы однородная компонента — это как раз множество всех многочленов в степени ровно t. Однородных многочленов в степени ровно t. Поэтому, ну, тут слово однородное — это просто название, как бы по аналогии с однородным многочленом. So let us prove something about this function. So this is induction on the number of generators. So we start with the case that the number of generators is just 0. Yeah? So n is equal to 0. But since m is finitely generated over A, which is equal to A0. Yeah? So it shows that the number of non-zero components is finite. Yeah? So that n is equal to 0, this means that s is equal to 0, the number of variables. So, so we have no components, so you have the property that A is equal to 0. So if you look at M, which is the sum of Mi, yes, so you see that you cannot have, since you are generating over A0, so it keeps all the components, so A0 maps mi to mi, but yes, so multiplication by 0. So this means that M has only finite number of non-zero components. So F M has finite number of non-zero components and has finite number of non-zero components. So this implies that M, so that P is a polynomial, yes, so that because it contains only a finite number of non-zero variables, it's just polynomial. So what you yeah, so then we just want to speak about induction. So notice that just if you look at A, so at A itself, yeah, so you can think of polynomial ring, yeah, that maps to A by our A. So this is surjective map, xi maps to the corresponding generators. So if you think of M, you can think it about as a module, but it is more convenient to make it a graded module. So we can consider M as a graded module over the polynomial ring. Yeah, so here it is like you are thinking about, so if you think about variety, yes, so you may, in more general in algebraic geometry, you may think of the algebra functions as the function on variety, but so the polynomials modular relations, modular ideal, but the variety is embedded in a finite space. So this is this map is just, you may think of as embedding of your variety that you want to consider in some fixed affine space. And now you have the following property. So you have a multiplication by excess. So on module, you have multiplication by excess. So you have quotient. Yeah, so this is yeah, so in general you have exact sequence of yes, let me just yeah, so you have module M. You can consider multiplication by the last variable, and you can consider quotient. So this is cokernel. Cokernel is the quotient by the image. So it is just M modulo X S M. This is yes, or notice. So this is a cokernel of the multiplication by excess. And you can also consider kernel. Yes, so K is a kernel. So it is a kernel of multiplication by excess. And notice that this excess is homogeneous
variable, so you have a natural grading on M, and it reduces to the natural grading on the quotient, and you have a grading on the kernel. Yeah, so L is decomposed into the sum of LK, and K is also decomposed into the sum of K, since the element is graded. Otherwise, you cannot say. And you can track on the graded pieces how they map to each other, and of course the graded piece Mn is mapped to the corresponding piece Mn plus Ks. So this is multiplication by excess. So here in the co-kernel you have the same grading as here, so you have L n plus Ks. And here you have Kn as the kernel. So what we have? So first of all, you have to notice that, of course, if you think of, so K is a submodule. Yes, so notice that if you look at K, so is also A0, x1, x s minus 1 module, because this is just quotient of A modulo xs, so since the reason is that it is modulo over this ring is just because xs acts trivially. And also, what about co-kernel? Co-kernel by multiplication. On co-kernel, the x multiplication by x also, so so L is also A0 x1 xs minus. For the kernel, it is just by definition. For co-kernel, so if you take M, the element of M, yeah, so it maps to, so yeah, so since xs acts trivially, and M maps to xs, M. Yeah, and it is 0, so it is equal to 0 modulo xsm, yeah? Modulo divisible elements. So you see that kernel and co-kernel are just modules over the algebra with smaller number of variables. So we can guess that you can use induction here. So so notice, yeah, so first notice that for lambda, we have the following, so lambda of k n is equal to plus то есть вот если вот у нас есть точная последовательность из 4 членов, so if you have a 4-term exact sequence, so alternating sum of function of so if you have a function that is additive on short exact sequences, and you take a long exact sequence, so the alternating sum will be 0. So here I can take the sum of this and this, and the sum of this, it should be equal to the sum of this term and this one. So let me write this down.
Да, пояснить, почему вот как бы вот это равенство, да? Надо?
Why is happening?
Ну давайте поясню. So if, ну по крайней мере для четырехчленной поясню, а для более длинной вы сами увидите, как это сделать. Смотрите, so if you look, if you have, дайте, может даже для любой нарисую, потому что это вот, как бы, когда я с этим столкнулся, мне было не очевидно, как это можно нарисовать, поэтому меня очень обрадовало это. So you have a complex, so suppose it is exact, meaning that, so here is phi 1, phi 2, phi 3, phi 4, phi 6, etc. Oh, just, yeah, phi 5. So if, so suppose this is 0, yeah? So now what you have, so here you have, so this thing is about the splitting of short exact sequences to the long exact, of long exact sequences into the short exact sequences. And it is drawn as follows. So here you see that the map is surjective because kernel of phi is equal to the image of phi 2. Then you have the following. So here you have image of phi 3. And this sequence is exact. So I draw like this. And in the same way, it is, yeah, so the image of phi 3 is equal to the kernel of phi 2. Yeah? So, да? То есть, ну, как бы это есть точность, да? И поэтому я как бы пишу, что ну, вот это вот, ядро вкладывается в C2, и ну, как бы оно факторизуется при переходе в C1. Вот это как бы я пишу вот так точно последний.
Может быть такие штуки сверху?
Да, тут можно вот так дорисовать, потому что ну, C3 отображается в свой образ surjectivно. So C3 goes into its image surjectively. And here you again can draw kernel for phi 3. Не, ну вот для вот этого, да? Ну как бы образ C3 это фактор C3 по его ядру. Это по φ3. А это образ φ4. И тут мы рисуем вот так. То есть вот в эту сторону вот так. И мы используем образ. А вот эту сторону мы используем ядро. Поэтому мы пишем вот такое расщепление. И дальше вот как бы мы пишем дальше вот эти вот штуки. And so you see for when you calculate for lambda, you see that lambda of C2 is equal to what? From this is lambda of kernel of phi 2 plus lambda of image of phi 2. This is C1. So then you draw, you do the same for C3. Yes, so that you are drawing lambda of C3 is what? It is image of lambda of image of phi 3 which is this equality plus lambda of kernel of phi 3. Ну и тут можно как бы написать лямбда от C4 это. Тут я специально напишу, ну поскольку у нас φ3 равно φ4, я напишу образ под ядром. So I shall put image of phi 4 plus lambda of kernel of phi 5, yeah, etc. And yeah, so here you have equality here between these terms, and this will be alternating. So here you will have equality like this if I write down, and then I will have equality between these terms. So you see that sum of alternating, alternating sum of these equalities gives you 0. Yeah? So lambda ci gives you, well, the right hand side gives you 0 because the terms are cancelling. Yeah. So actually, yeah, so the only thing that maybe the last term should be something like this, C1 on this side and C1 on that side. Yeah, so you should start by, formally you should start with lambda of C1 and write it down like here you have lambda of C1 that should be cancelled with this term and of course this should be finite sequence here. So the last step, the lambda of C1 is image of Phi1, lambda of image of Phi1. It should end on the kernel. That will be also the last element in the sequence. So you have alternating sum is equal to 0. So just corollary is that. Yeah, so and now we have to so figure out about this. Yeah, so let us write down again what sequence do you have, and this should be a little bit interpreted because you have lambda of kn, yeah, so plus lambda of m and plus ks equal to lambda of mn plus lambda of ln plus ks. And notice that we are somehow in yeah, so if you write down Poincare series, so what do we get? So notice that yeah, so when you form Poincare series, yeah, so when you want to form Poincare series of this form, yeah, so this yeah, so we have to interpret all terms in the formula. So here notice that yeah, so notice that in order, so if you look at this term, it looks like lambda of nm plus ks. So this term should be multiplied by t n plus ks. Yeah? So this will give you a Poincare series. So when you take this, so in order, so at least we multiply this equality. So this term has highest degree. Yeah. So we multiply this equality by t n plus ks. Yeah. So we multiply it by t n plus ks. And we summate, yeah? So the problem is that so this gives you Poincare series. But the term starts with if you summate over n starting with n0, yes, so the first term is not zero term, it is the summation, and let me write it down. So summate with respect to m. So it gives you Poincare series without first ks terms. So we have to. This means that we have to.
Начинаем суммировать просто.
Что?
Мы просто начинаем суммировать.
Мы начинаем суммировать с не нуля, но с n равно нулю, но слагаемые, которые здесь возникают, они стартуют с ks. Да? Поэтому, как бы, значит, это можно записать как тот элемент, который остается, это pmt минус g от t полином степени меньше ks. Да? So degree of g of t is less than ks. So we can write down the sum over mks as this polynomial.
What is GT?
Huh?
What is GT?
Some polynomial, I mean, so if you summate this, yeah, so if you summate this one, yeah, so this will, the sum will be like this. It starts with n equal to 0 to infinity of lambda m n plus ks t times n plus ks. This can be written as the sum starting with I larger or equal than ks to infinity lambda m lambda mi ti. Yeah, so it's not Poincare series, yeah, because it starts with ks.
Yes.
But the first part, so it is equal to Poincare series plus some polynomial.
Yes. Okay.
Well, actually minus some polynomial, but it doesn't matter. Minus g of t, where degree g of t is less than ks. Okay?
Okay.
So then about lambda k, so this is just this gives you the module. So the Poincare series for k. Yeah, and this the right hand side. So this mn is notice that mn is not exactly Poincare series because it looks like the term mn gives you the series. So this one gives you the series of the form lambda mn t n plus ks. Yeah. So the sum over when n is equal to 0 to infinity. This term has all kind of summands, but it has larger degree with respect to t. So this is just the first Poincare series of m times t to the power k. Yeah? Okay. So this you write down this is Poincare series, Poincare t times ks, Poincare series of m. And then you just use Poincare series
of Poincare series of Ln plus Ks of Lt. So here, if you like, of course, you can do the same thing. I mean, you can put, yeah, so here, but I mean, so here it doesn't matter, just it is just, let us denote this by Poincare series. So what do we have? Yeah, so actually, here you can make a shift to the kernel, yeah, so that of this variable, and then this implies that you have putting this to the right hand and to the left hand side, you are putting p of m times 1 minus t to the power d. I have just realized that I have mixed indices. Just let me put powers of variables to be k. So since I have just, so I wanted to change it for d, but in my notation I had ks, so let me put it ki variables of degree ki. Да, тут я уже пошел. Да, и смотрите, ну то есть как бы, что у нас остается? Ну то есть у нас тут как бы возникает, что сам ряд Poincare умножается на, so the Poincare series multiplies by 1 minus t ks, and here you have Poincare series that looks like p of lt plus p of k t tks and plus g of t. So you see by induction, so these are rational. So this by induction can be written as some polynomials f tilde of t divided by the product of so since L and K are modules over algebra with smaller number of variables, x1, etc., x s minus 1. Yeah, so you may write them as the product just.
It will be minus pkt.
Hmm?
It will be minus pkt.
Чего? What?
In that line, it will be minus, I mean plt minus pkt.
Yeah. There should be a minus. Yeah, precisely. But of course it is minus, but for the statement it doesn't matter because I mean it is important for calculation, for inductive calculation, but not for our answer for on the problem that these functions look like polynomial divided by this fraction, And so GT is just a polynomial. So you see that possibly. So this means that GT can appear in this denominator by multiplying by this sufficiently large polynomial. So GT is a polynomial of degree less or equal to than KS. Yeah. So you are multiplying it by the polynomial of degree sum of the degrees. Yeah. So you may also see that degree of polynomial of ft is less or equal than the sum of degrees of these variables. So this implies that EM is just f of t divided by the product of s minus 1, 1 minus t. However, so this, so when you do not have the problem is that you can reduce it to the zero induction step, where you just have a finitely generated module, where you have, you know that this polynomial is just. I mean, when you are doing induction, you can bound the degree of f via degrees of these guys and the sum of. So maybe let me write this down, that degree of ft is less or equal, so that degree of L. So maximum of degree of L, degree of K plus Ks, or so degree of G of T, which is sum of Ki's, yeah? Where I is equal to 1 till S. So so here you can write it down minus 1. So here, but you see that you can reduce. So this term is more or less constant. Yes, I mean it depends only on the number of variables. But clearly, when you reduce to a module over the ring with when you have when it consists only on A0 and doesn't have generators, these modules can be arbitrary. The module can be arbitrary, so that means that you can use this bound, but only if you know this for 0. There is no absolute bound. It depends on the module. And so this shows that this Hilbert polynomial. So let me do some consequences, and so we have to derive something about this. So additionally, it is convenient to use this. So assume that now. Additionally, assume that all degrees ki's are equal to 1 for any I. So that means that, as I said, that the algebra is generated by this first component. So this simplifies a little bit the polynomial, because it now looks like all variables has degree 1. So this is just f of t divided by 1 minus t in the degree d, where d is, well, s, you had s, sorry. S is the number of generators.
Then the trick is the following, to write down what is 1 minus TD. So you can write it down as series, binomial series. So let me use D now. So, just. То есть это вот, this calculation, notice that this calculation is just for free algebra. Yeah, so this is just calculation for. Also notice that you can just so as an exercise. Calculate that I think will give you as in the second sheet. So calculate Poincare series for k x0 row x1 xd. Yeah.
Кстати, а когда вообще второй набор задач появится?
Ну вот я, ну прям вот сегодня-завтра. И я уже экзаменационные задачи тоже выложил уже. Да.
Нужно будет решать и сдать.
Да.
Так же. То есть, по сути, просто третий листок.
Да. Ну, да, считайте, как третий листок, просто он с большим весом. Ну, потому что в первых двух я не так сильно подбирал задачи.
Ну, потому что упражнения.
Ну, как бы, да. А ну, как бы в экзамене больше, чтобы они были более содержательные. Вот, соответственно, so this is just calculating series, so you can notice what are binomial coefficients, of course, yeah. So that are precise that calculated our monomials. And sometimes when you do something combinatorics with general combinatoric objects, you can obtain, so if you, for example, it also is, it is good to do in group theory. Yeah? So a priori, you prove something for geometric, some equalities for geometric objects like Hilbert polynomial of an algebra. It has some properties, and you can calculate it very easily for some precise algebra, and it gives you the consequence. So, for example, you can calculate it in two ways. Once via our algorithm, or with just simply using binomial coefficients by definition. And this gives you two different properties of the object, and you can compare formulas to get some non-trivial combinatoric identity. And if you want to multiply by some polynomial f of t, it looks like, so the polynomial has integer coefficients, so it is just the product of AI, TI. And you may put it, so if you compare coefficients, so lambda of Mn, so of the corresponding module will look like this. So it will be a sum from I equal to 0 to n, AI d plus n minus I minus 1. D minus 1. And this notice that these guys, So precisely these binomial coefficients are polynomials in N, and they are characterized by the following property that they take integer values for on integer numbers. So they take integer values on integer numbers. So you see, for example, that the binomial coefficients give you a polynomial with non-integer coefficients, but with the property that it gives you integer values on integer numbers. And you may prove easily that binomial coefficients are exactly the basis, if you think of them as polynomial in N. You may prove that they are basis, integer basis for polynomials that takes integer coefficients on integer numbers. So this gives you the way you represent the series, and as a byproduct of the proof, you see that these are polynomials. So these are polynomials. In N. And yeah, so maybe today I shall finish, and next time I shall introduce dimension. So I shall compare this with group dimension, and so first of all we have to see what are precisely these filtrations, and we shall introduce the notion of dimension related with Poincare series. And we shall see that this is related with our proof dimension because we will compare it with the system of parameters for our dimension.